Yeah, I'm good.
Good stuff. Okay, so we're going to pick up some pieces on redox reactions. But firstly, I just wanted to see your general understanding of it before we move on to what you wanted to look at in terms of redox reactions in acidic conditions and such. Yeah, on half equations and
Yeah.
all that good stuff. Okay, right. So maybe just as a bit of an intro, I'm sure you probably know already, of course, then what this concept involves, and it involves using oxidation states. Yeah. So when
Yeah.
we talk about a redox reaction, it's one where there's both reduction and oxidation. Now, reduction, of course, you remember is, what is reduction? Is it gain or loss of electrons?
Gain.
It is gain, and oxidation is therefore loss. You're absolutely right. And we use the acronym oil rig. Oops, let's go here. Yeah, oil rig. Okay. So in this case, that's just an example. You've got copper sulfate reacting with zinc, okay, and then you've got copper plus zinc sulfate. What kind of reaction is this, by the way?
A redox reaction.
Redox, but there's another name as well for it.
Um, is it displacement?
You're absolutely on the money. So this is a displacement reaction, which is also a redox reaction, because when we look at this, we can see that the copper goes from +2 to 0. So to go from +2 to 0, it means it must have gained electrons, because +2 means it had lost. You happy with that? So the copper
Yeah.
is reduced and the zinc is oxidized. We've gone from it being to 0 to +2. So therefore, it's a redox reaction. Now, have you heard of a disproportionation reaction?
Yeah, I think so.
Yeah, so this is where you have a species both simultaneously oxidized and reduced. And here's an example where you have chlorine. Okay, so here an element, of course, is 0, and a molecule such as chlorine here, okay, diatomic has also 0. Just key to remember that. Okay, and then of course, what we see here is the water. The hydrogen is +1 and the oxygen is -2. And we do the same as well on the other side, where we see that the chlorine here has -1. Now, the reason why it has -1, remember that this is more electronegative, okay? So the higher the electronegativity, that means that it takes on a negative oxidation state. Are you happy with that?
Yeah.
Okay, good. Then now we come here and we'll have a look here and see what's happened. So here, of course, we now have the chlorine at, if you look carefully, which is at a +1, okay? And this here is also at a +1. Now, if we look at electronegativities, well, the oxygen is still, oops, oxygen is still -2, by the way. Now, what you also
Yeah.
notice is that when we add all the oxidation numbers, we get 0, yeah? That's another key thing to note here, all right? So here we can see that the chlorine in one case has moved from 0 to -1 and also from 0 to +1. So this is what we call a disproportionation reaction, because the species has been both oxidized and reduced. So here are a few for you that I'd like you to tackle. Okay, now I have sent this sheet as well via your email. So you can open that. If you go into your email, you would have seen one that said worksheet for today.
Yeah. Okay.
Yeah, okay. So let's have a go at this, all right? So we'll have a go at maybe the first three, just see how you cope with that. Make sure that you're okay with the oxidation states. So there's a bit of an example here for you just to show you how you can go about laying out your work if you so wish, okay?
Okay.
All right, so I'll go at the first two first.
can both the sodium and the hydrogen be the species that are reduced?
Are you looking at question 1?
Yeah.
Okay, so you're saying they've been reduced. Okay, so let's just take this one together then, shall we?
Okay.
And you see what you did. So you've got your Na. So, well, if we just list what's listed here, we've got Na, yeah, and we have got H, and we have got, what else do we have? Oxygen. Yeah?
Yeah.
So oxidation state of the Na in this side is what?
2.
Not quite.
Oh, oh wait. Is it minus +1?
Very good. It's in group 1.
Yeah, I just assumed because of the 2, so I just added them both.
But there's 2 of them. So there's a total of +2 versus the oxygen. Yeah. In this case, the oxygen is going to be -2.
-2. Yeah.
Yeah. Okay. No worries. And then what about the hydrogen in this case? What's the hydrogen at?
+1.
Very good. And the oxygen?
-2.
Yeah, so it's -2 in both instances. It's -2. Now I look at this side, okay, of this side of the equation. What's the oxidation state of sodium?
Is it still +1?
+1, very good. Okay. What about that of the hydrogen?
+1.
+1. What about that of the oxygen?
-2.
-2. So can you see, same numbers, isn't it?
Yeah.
Therefore, is this a redox reaction?
Yeah.
Think very carefully. Has anything changed its oxidation state?
No.
Yeah, that has gone from there. Nothing has changed its oxidation state. So this is not a redox reaction. Does that make sense?
Yeah.
Very good. So you will get these kind of questions in your multiple choice to say which of these reactions is not a redox reaction. So this is a process you'd use. Okay.
Okay.
Have I got number 2 then? Show you number 2. So another hint, Zinera, to help you, think about oxidation states as ionic numbers. So think about each of these things as ions, unless of course it's in an element state, okay? So
Okay.
think of them as ions. So here, if you had to write this as the ions present, you would say I've got 2 Na plus and I've got O2 minus, okay? So this is telling you that that's oxidation state +1 and oxygen is -2, okay?
Okay.
All right, likewise, think of the water as being composed of 2H plus O2 minus. And again, this is 2Na plus 2OH minus. Okay?
Okay.
And then you can split these. So what would give this a minus charge? Well, that's because this has got an oxidation state of -2, and the hydrogen has got an oxidation state of +1. That's what's creating this minus charge. That's another way to think about it, all right?
Okay.
Okay, good.
Is this not a redox reaction?
Well done, excellent, beautifully done. Okay, excellent, well done. So do we take that one? Okay, and getting the idea. Now have a go at number 3.
Is this one a redox reaction?
It is a redox reaction, but a redox with a twist. Yeah? So
Yeah.
if we just analyze this together and see what you did. So you obviously wrote your H. Yeah?
Yeah.
Good. And your O. And of course, then we write the oxidation states. Now, what would be the oxidation state of hydrogen? Well, it's +1. Yeah. What's the oxidation state of oxygen?
-2.
Ah, now this is a confusing one, isn't it?
Yeah.
This is really confusing. So let's look at it together. So remember, the overall charge must be 0, isn't it?
Yeah.
If you're thinking about it as an ion, overall charge is equal to 0. So if each of these hydrogens have a charge of +1, so you have a total charge of what? From these hydrogens? +2.
Yeah.
And what should the total charge then supplied by these 2 oxygens be?
If it needs to equal 0, it should be +2. -2.
Good, very good. So if it is -2, so just like here, so to find the oxidation state of hydrogen, you would say, of one hydrogen, you'd say 2 divided by 2, and that's your +1. So what would you do to find the oxidation state of oxygen in this case? -2 divided by 2. So it's -1 on this side of the reaction.
Oh, I did it the other way around. I did the hydrogen is +2.
Okay, so you got to think about them in ionic form. So hydrogen only has one outer electron, so it can only lose one.
Yeah.
So its oxidation state will always be +1. I mean, there are cases when the oxidation state of hydrogen is -1. So if you had a compound such as sodium hydride, this here, the oxidation state of the sodium is +1 and the oxidation state is -1. You rarely see these type of questions, but just keep in mind. So this is, for example, e.g. sodium hydride. Okay, but generally 9 out of 10 times, hydrogen is a +1. And for the oxygen, did you see how we worked out the oxidation state? Yeah.
Yeah.
So we looked at the overall charge, it has to be 0. We know these guys are going to give a charge of +2. Therefore, this must be a total charge of -2. Because they're 2 oxygens, it means each one has got an oxidation state of -1. Yeah? Now we come over here. So what's the oxidation state of hydrogen in here?
+1.
Very good. And what's the oxidation state of oxygen?
-2.
-2, well done. What about the oxidation state of this oxygen here?
0.
0. So what's happened to the oxygen? It's gone from -1,
Yeah.
and it's gone to both -2 and
0.
0. So what do we call that?
A disproportionation.
Correct. So you've got to put a tick in this box. Let's get a red pen. Okay. And we can also see, is there anything else that has happened? Well, redox has happened as well because there's been reduction and oxidation. So we can tick that box as well. Are you okay with that?
Yeah.
Yeah, but it is fundamentally a disproportionation reaction. Now, which species was oxidized in this case? Well, the species that was oxidized is H2O2. We only have one thing on the left-hand side. Yeah?
Yeah.
Species was reduced. Well, it was H2O2 again, because it's a disproportionation reaction. So the same thing has been oxidized and reduced. So which is your oxidizing agent?
H2O2.
Correct, the hydrogen peroxide. And likewise, the reducing agent is also the hydrogen peroxide. Does that make sense?
Yeah.
Good. Okay, we're getting good at these. Another one for good measure.
Um, is this a redox reaction?
Yeah,
And
it's a
the
redox. Very good.
yeah, the shall
Any
I just say
disproportionation?
I don't think so.
Well done. Good. Okay. And what is the species that's oxidized?
The SO2.
Spot on. Well done. Okay. And which is the species that's reduced?
The O2.
Good. Well done. And which is the oxidizing agent?
Is that the O2?
Oh, absolutely. So remember, the species that's reduced is the oxidizing agent.
Yeah.
Okay, because reduction is gain. Yeah. So the species that is reduced will therefore receive electrons. Yeah.
Yeah.
Okay. And then for the next one, reducing agent.
The SO2.
Correct. Okay. Well done. Okay. One last one, Zinera, and then I'll let you do the others for homework. Okay. So you've got 6 up to 10. So you got, yeah, 5 more, which you can do as a piece of homework. I might even leave that one actually number 5, and we'll go to something a little bit more challenging here, just to wrap up. So I'll leave this as a bit of a homework. Okay. And if we go to the next page, okay. So we got this one here, number 9.
is the nitrogen what is oxidized and the Cr what is reduced?
And the CR is reduced. So is it a redox reaction?
Yes.
Good. Okay. Now this, I'll be very interested to see. Obviously, I can't see what you've got, but did you have the oxidation state of the nitrogen? What was the oxidation state of the nitrogen this side?
It was -4.
Not quite. So this is a bit tricky, and that's why I wanted to have a look at it with you. Okay. So we can see that we've got an ammonium ion there, isn't it? NH4, right?
Yeah.
What's the charge on an ammonium ion? Can you remember?
Okay, wait. Is it just minus?
Not quite. So a hydroxide ion has what charge on it? A hydroxide ion.
Minus.
Good. What about a carbonate?
Was that plus?
Not quite.
Minus.
2 minus. What about a sulfate?
SO42 minus.
Very good. Okay. What about the next one then? Ammonia, ammonium?
The NH 4 plus.
Well done. So memorize these. You need to know these, okay? Now they're very important, especially in a situation like this. So you can see that because you've got 2 ammonium ions, what will be the total charge contributed from this?
+1.
Not quite, there's 2 of them.
Oh, +2.
+2, well done. So what will be the charge on the chromate ion? This is the chromate ion.
-2.
-2. So all of this must equal -2. Correct. Well done. Okay. Now, if we just look at this and just use the ammonium ion, we can use it to work out the oxidation state of the nitrogen. So what do you reckon the oxidation state of the nitrogen would be?
Would it be
If the overall charge is +1?
would it be neg -2?
Not quite, nearly there. How many hydrogens do you have?
A 4
4, and each hydrogen has a plus charge. So you have
yeah.
+4 added to
Oh,
something.
3.
Not quite. Try again.
-3.
-3. Well done. Okay. So this is -3. Okay. Now it goes on to this side. What's the oxidation number for nitrogen this side?
0.
Very good. Then you have your hydrogen. Your hydrogen is a +1. There's no changes to that one. And on the other side, it is also a +1. Then your chromate ion. Now, what's the oxidation state of your chromate here?
Is it +2? Oh, +6.
+6, well done, excellent. And again, same logic. There's 7, each one has got -2, so I've got -14. So -14, okay, this added to 2x, because there's 2 of them, gives me -2. Therefore, what should x be? So you get on the other side, yeah, 12, because -14 goes to the other side. So you get 12, so you get 2x equals to 12. So each one must be a +6. So that's the way you get your +6. Okay, good. And then on the other side, if we look here, what is the oxidation state of the chromium?
Is it 3?
Very good, +3. Okay, so you can see that this has been oxidized, the nitrogen. This has been chromate, or the chromium has been reduced. So it is a redox reaction. We can look at the oxygen if we wanted to, but nothing much happens to the oxygen anyway, okay? And I'll let you fill in the other blanks as a piece of homework. But did you follow how we went on to establish the oxidation state of nitrogen and that of chromium? Did you follow that?
Yeah.
Very good. Okay, good stuff. This is very important groundwork in us moving on to what we want to start looking at now, which is acids. The rest of them, by the way, are all homework questions for you to have a go at. Okay, so oxidation states. So the key thing I said, when using oxidation states, we effectively imagine everything to be an ion. It's very important. So the oxidation state is the charge it would have if it was an ion. Okay?
Yeah.
So simple ions, there you go, Cu2 plus oxidation state plus 2, Cl minus, minus 1, Al2O3. Again, you think about this in terms of ions, the overall charge on this would be 0. So if that overall charge is 0, and we know that this is minus 2, so this would give us minus 6, this would give us plus 6 and minus 6, yeah, because of these oxidation states give us 0, which is what we said already. In elements, the oxidation state is 0. So these are the rules, the ground rules we're laying here so that we can, okay? The total of all the oxidation states must always equal the overall charge on the species. So if it is charged, then the total oxidation states must equal the overall charge. So in molecules of more complex ion, the more electronegative, and this was the part I raised early on, is assumed to be the negative ion, okay? Now, H is nearly always, now I gave you an example where it is not +1. Can you remember that example?
In hydrogen peroxide.
Not quite. In sodium hydride. So in hydrogen peroxide, this is still +1, okay?
Okay.
But in sodium hydride, we assume that the sodium is what donates the electron to the hydrogen. So this is -1 and this is +1. But that's a very rare case. H is nearly always +1. That is the exception. I'll write again, exception. Okay? Then the next thing we do is calculate the oxidation state of the element, or the stated element. Oh, well, this is a bit of an example anyway here. Calculate the oxidation state of the stated element in the following species. Okay, we're just going to throw a few here. So here we've got FeH2O6 2+. Okay, so calculate of the stated element. So we want the oxidation state of the ion in this case. What do you reckon the oxidation state of ion is in this particular species? Using the rules we've just spoken about.
Is it just 2+?
Very good. Excellent. Okay. And there are some more here for practice, which I would like you to go through at some stage as well. And we're going to have a quick review. Now writing half equations. Okay. And this is where we were looking at acidic conditions and such. So this is the part that a lot of students find a bit hard. Okay. But because we've laid a foundation, hopefully it shouldn't be so bad. So imagine you were told that you had a compound, okay, vanadium oxide, yeah, and it's an ion of vanadium oxide, and a vanadium oxide ion, and it gives you another vanadium oxide ion with a different oxidation state. So imagine we wanted to write a half equation for this. The first thing we do is first we write the oxidation states of, well, we start off with the vanadium, okay? We can see that in this case, the vanadium has an oxidation state of +4. Yeah, you're happy with that?
Yeah.
Whereas in this state, it has an oxidation state of +5. The reason why it must have a +4 here is because the oxygen always has an oxidation state of 2-. So if you've got a 2+, it means this must be what? +4. You okay with that?
Yeah.
Good. All right. Then the next part of the rule is that we balance the element that is changing the oxidation state. So you can see here that the vanadium has gone from +4 to +5. How can it go from +4 to +5? Only if it loses an electron.
Yeah.
To go from an oxidation state of +4 to +5 means that you have lost an electron, because oxidation is loss.
Yeah.
So far, so good?
Yeah.
Good. So to show that, well, I can write it and say this VO2 plus has lost one electron to form VO2 plus, as in, okay, just looking at the oxidation state of the vanadium. But this is not a good presentation. Normally, or AQA advise that where you have something being subtracted, you take it to the other side of the equation so that it becomes positive. Are you okay with that?
Yeah.
Very good. Now we're going on to the latter parts. Now here, we now need to sort out these oxygens, because we see we've got oxygens this side that are not balanced with the oxygens on this side. So for every ore gained, we need to add an H2O molecule. It's very important, this rule. So can you see that moving from here to there, I've gained one oxygen?
Yeah.
Good. So I need to add a plus H2O on the left-hand side. If I had lost an oxygen, I would have had an H2O on this other side. But because of gain going from left to right, I add my water on the left-hand side. Now we're getting somewhere. So I can see, well, I've got how many oxygens on my left-hand side? 1, 2. Yeah?
Yeah.
And how many oxygens on my right-hand side? 2 as well. Yeah?
Yeah.
But I've got hydrogens on my left-hand side and no hydrogens on my right-hand side. So to sort that out, to sort the hydrogens out, okay, because I've gained hydrogens on the left-hand side, I need to gain some hydrogen ions, and I use H plus ions on the right-hand side. Are you following so far?
Yeah.
Very good. Now, when we look at this, the next last part, which is super critical, is this. Do not forget this part. Check that the total electric charge on the left-hand side equals the charge on the right. If they're not, then you have gone or you've made a mistake. So let's look here. We have a total charge of how much on this side? 2 plus.
Yeah.
What about the total charge this side? Well, this is a +1, and this is a -1. And this here is 2 protons. Well, hydrogen ion is a proton, so this is a total of +2. These cancel off because it's +1 -1. So you can see I've got 2 plus on this side, and I've also got 2 plus on the right-hand side. So far, so good?
Yeah.
Good. Now let's look at another example. Again, going through the rules. Here we have a bromate ion. And again, we start off with the Br, because we don't have an oxygen this side per se, so we're going to work with the Br. It goes from +5, which should be, because if this is 3 oxygens and each one is -2, so you get -6. To have an over a -1, you must be adding a +5. So this must be +5. I've gone from +5 to 0. What's happened to my bromate for me to go to +5 to 0? It has been reduced. Are you okay with that?
Yeah.
Yeah? Then the next thing I do is I balance. Because you can see I've only got 1 bromine atom here, but I've got how many on this side? 2. So I balance my bromate. So to do that, I put a 2 in front. So far, so good?
Yeah.
Good. Now then, because I know that for a bromate ion to go from +5 to 0, what does it need to do? It needs to gain, because it's been reduced, isn't it?
Yeah.
But that will be for 1 bromine. Now I've introduced the 2. So how many electrons am I going to need?
10.
10, because I've got 2 bromines, and each bromine receives 5. And if there's 2 lots of them, so I've got 10. Now the next step is I need to sort out the what? The oxygens. So if there's an oxygen on the left-hand side, to counter that, what should I do? I should introduce water.
Yeah.
Now, how many oxygens do I have this side? 2 times 3. How many do I have?
Um, 6.
6. So the water I'll introduce will have 6 H2O. This is so I can cancel out the oxygens. Are you happy with that?
Yeah.
Good. Now I need to deal with these hydrogens in the water. So to do that, I need to add hydrogens on the left-hand side. You're always trying to balance it almost.
Yeah.
Now, each of these here, if there are 6 H2s, when these become ions, these would come from the acid, and that is what we were talking about. So how many do I need? I'll need 6 times 2, which gives me 12 on the other side. Now that I've done that, I need to check that my charges balance. Okay, so I've got -2. I've got, this is 10 electrons, so -10. Okay, and this is 12 positives plus 12. And I see that I get 0 overall. And if I look at the charge overall this side, it's also what?
0.
It's also 0. And that is all there is to it. But of course, these things always look easy when explained. It's when you then have to deal with the problems that then you kind of learn a little bit more. And of course, we're then going to look at combining equations as well. So just as a simple one first, very, very simple. Let's start off with 3a. How would you write it for 3 part A? We're just going to start off easy. In the AQA likes.
Would you do Na first, then Na plus first E?
Correct.
Yeah, minus.
Correct. We need that minus. Can you see the total charges? This side is 0, and the total charge on this side is
0.
0 as well. Okay. Likewise, let's have a go at B.
Would you just add would you add 2E minus to the right side?
To the right side or the left side?
To the left
What's happened?
side.
Has it gone from +4 to +2? Has it been reduced or oxidized?
It's been reduced.
So where should I add the electrons? On the left hand side or the right hand side?
The left.
Correct. Well done. Okay, good. Now that you've done these, we're going to move on to something which is more relevant to what you wanted. Have we got part E? Trying to follow through with the rules.
Is it CR2O7 2 minus?
Yeah, 2 minus. Well done.
Plus,
So far, so good. Yeah.
plus 14H plus.
Good.
And then the arrow
Yeah.
CR3 plus.
CR3 plus.
Plus 5E minus.
Plus 5E minus.
Plus 7H2O.
Plus 7H2O. Okay. You got some parts of it right, and you stumbled on some parts. Now, I'm also going to show you another. Now, I don't know if you've been shown this as a little shortcut, but I'm going to have to show you a bit of a shortcut here because I can see a blank page after current. Okay. We're going to do it slightly differently here. Pretty much the same procedure. It's just to end, just to make your life a little bit easy. So I've got CR2O7 2 minus gives CR3 plus. So already here, firstly, what I notice is I've got one CR and I've got 2 this side. So what should I do with this? Put a 2 here.
Yeah.
Very good. Okay, so far so good. Yeah. So I need that just so I can balance the chromiums. Okay. Then the next thing I do is, I know I've got oxygens here. By the way, I'm just going to put it over here as a quick little way of doing it. I've got oxygens this side. So what am I going to have to put on the other side to counteract those oxygens?
H2O.
H2O, very good. And what number should I put against the H2O to balance it so I have the same number of oxygens?
7.
7, well done, good. Okay, so I'm going to put a 7H2O. Okay. Now I've got hydrogens this side. I need to balance them with something on the other side, which can remove those. So what am I going to have on the other side?
14H plus.
Well done. Excellent. Now the next step is the next step, which is the shortcut. If you're not sure how many electrons and you lost, this is going to be your little saving grace here. Now, what's the total charge on the right-hand side?
3 plus.
Not quite. Each chromate has 3 plus and you've got 2 of them. So what's the total?
6 plus.
Well done. So you have to be absolutely on it. Don't just observe this. Look at the number in front, multiply. Okay? Good.
Okay.
Now, what's the total charge on this side of things?
-1.
Not quite. How many positives do you have? So don't forget.
Oh, 14.
Thank you. So what's the total? You've got to use all the charges. What's the total charge? Very good. And it's plus 12. All right? Plus 12. What do you need to add either on either side so that the numbers are balanced? So you've got a big number here, plus 12, and you've got plus 6. Yeah?
Yeah.
So in terms of electrons are, what is the charge on an electron?
Minus.
-1. So I'm going to have to add, where should I add the electrons? This side. Can you see why?
Yeah.
Because then I can bring and reduce this down to 6. So what number do I need to put in terms of electrons?
6 E minus.
Very good. And that's it, Bob's your uncle. Okay?
Okay.
So that method, if you are lost, you could have gone about it using to say, well, look at the oxidation states and you'd have come up to 6. But I've shown you a much quicker method if you really run out of time in your exam and you want to do this pretty quickly. Right, okay, we're going to throw in one more for good measure then, shall we? Let's try and we might look at these in more detail because what I don't want to do is fully rush it. Is that okay?
Yeah.
Right?
Yeah.
Okay, let's look at F, shall we? As our last one.
Is it
Yeah.
SO4 2 minus 2 plus?
S. SO4. No, that's a minus, sorry.
Oh, okay.
Are you still okay with that?
I think there's a few changes.
Okay, have a go. It's a minus. S sulfate is always 2 minus. Remember? It can never ever
Yeah.
be a plus 2. Okay.
So
Yeah.
SO4 2 minus
Well done.
plus
Yeah.
8H plus
Plus,
8H plus.
I like the sound of that.
Then the arrow.
Okay.
S plus 2E minus.
S plus 2E minus.
Yeah.
Yeah.
Plus 4H2O.
Now, if I look at this, I've got a charge of, what's my charge I've got this side? I've got a charge of minus 2,
Yeah.
but the charge I've got this side, there's 8 positives, plus 8, and a
Yeah.
minus 2 gives me plus 6. So the charges are not balanced, so it can't be correct.
Then do you add um do you add 8 electrons to the left side?
Not quite. You're so nearly there. Let's go from where. So you've got your hydrogens, and now you're at this, and you've got plus 4H2O. Now you don't know how many electrons. All you know is that they always have to be added. Electrons always have to be added. So you've got to ask yourself, which side do I need to add them so that the charge is balanced? What's the total charge on the right-hand side?
2 minus.
Not quite. Remember, this is an element. There's nothing that's got a charge on this side.
0
0. Well done. What's the total charge this side?
plus 6.
Well done. Now, if I want to now add electrons, where should I add them? On the right-hand side or the left-hand side?
The left hand side.
Well done. And how many?
6.
Very good. And Bob's your uncle. Are you getting it?
Yeah.
Good. We're going to look at these in more detail, okay, in the next lesson, but we have made a start, and you're beginning to see that there's more than one way of doing it. Now, this is the shortcut method, the second method I've shown you. The first method was if you're doing it with rigor. This is just to save you time. So as long as you're accurate with your charges, you will be fine. And it saves you from having to look at all the different oxidation states and all that malarkey. Which do you prefer, the first method or the second?
The second.
Second is much, much more effective. Good. We will look at it in more detail and get some more practice on it. And of course, we've still got one more part, which is to look at combining half equations. But of course, this here, what you're seeing, this H plus is representing acidic conditions, okay? Which is what you wanted us to write, ionic half equations in acidic conditions, all right? So Zanira, we are a little bit over our time here anyway, but you have, you've shown, you've demonstrated to me that your understanding is beginning to pick up. So if you had to write this in your exam, you would have gained marks for this, 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 this. You'd have lost marks there. But we're getting there in terms of working charges. You're getting there. You're beginning to understand how to add charges. So that's what we're going to focus on in our next lesson. So you're absolutely certain when you add your charges and you know what your totals are. Is that all right?
Yeah.
Cool. I'll send you this board work and I'll send you the board work and yeah, you've got these questions for extra practice anyway. So try and have a go on your own. Watch the video if you need to, trying to listen back, rewinding, just on the tips and the tricks that you need. See how you get
Yeah.
on. And then in our next lesson, we're going to pick up on these, see how you got on, and then we're going to look at combining half equations. And then hopefully, depending on how the lesson goes, we can make a start on things like mechanisms and such. Is that all right?
Yeah.
Cool. So when would you like your next lesson then, Zanira?
As soon as possible or whenever you're free.
Okay, so today is Thursday. Trying to think realistically, can we try and perhaps push for Monday?
Yeah.
Because you don't start your exams until end of the month, isn't it?
Oh no, my chemistry exam's on the Thursday.
When is it? Oh, Thursday next week.
Yeah.
Oh my God. Oh, ooh. All right. So we're a bit. I kept thinking, oh, it's the other guy I'm tutoring for his maths. They don't start until end of the month. Right. So let's just have a look here. Then what do we have here? Yeah, 10. Do you want us to try and have? Ooh. Okay. Shall we pencil in tomorrow? What time do you finish? What time would be good? Would 6 p.m. be okay for you?
I can do it anytime tomorrow because I'm not at school this week.
Or you've got some kind of study leave, have you?
Yeah.
Okay, cool. So what I'll look to do then, if you're saying you can do it anytime, tomorrow I will look to helping you out. So let's see, I've got that. No, I can't do that there. But we can pick up pieces. I finish at my 10:03 and I am going to be at school, so the network can be a bit funny at school sometimes. I'm just thinking if I can give you a lesson during one of my free periods. But that doesn't start until, so 9, 10, so 10:15. So 10:15. Would you like to do maybe a session? Yeah, while this is fresh, I think it's better while everything is fresh, because if we leave it too long, then sometimes people tend to forget a few things. All right, cool. Shall we have a session tomorrow at 10:15? I'm going to do it from school.
Okay.
Is that okay?
Yeah.
All right, cool. No problems. I'll see you tomorrow at 10:15. Sorry, it's a bit of an early start, but I would imagine you're an early riser as well, aren't you?
Yeah.
You are good. Okay. All right, Sinira. I'll see you tomorrow at 10:15 then. Okay.
Bye.
Okay. Cheers. Bye-bye. Have a good evening. Bye.